In this video, we will cover how you use Prophecy to generate and evaluate predictions. As we've seen in earlier videos, Prophecy can generate predictions for two types of business cases. The first is the numerical business case. For example, how much business will this agent generate next quarter? And the typical form of these questions is how much, how big, how many, and so on. The second kind of business case is the categorical business case. For example, will this customer default next month? The questions can be of various forms, but the answer will be of the form true, false, yes, no, 0, 1, and so on. You use the same general list of steps to cover both of these types of business cases. You construct a predictive model, you evaluate and choose between predictive models, you generate predictions using new data, and then you evaluate how accurate those predictions were. However, the specifics of each of these steps will vary depending on the type of business case. For example, the metrics used for evaluating and differentiating model performance, or for evaluating prediction errors. Let's go into a little bit more detail on the differences of each step. Now, as we said, there are 4 steps: constructing the models, evaluating and choosing a model for predictions, generating predictions, and then evaluating these predictions for accuracy. Let's talk about the differences in each of these steps in numeric models versus categorical models. In the numeric model, you construct a model with a dependent variable that's continuous, a number. Categorical models, as we said before, will be of the form 0, 1, true, false, or yes, no. When evaluating whether a model is good or better than other models, the metric we use for numeric is the MSE, or mean squared error. You can look up the precise meaning of mean squared error, but in essence what it means is how far away from the correct answer is your estimated answer. In a categorical model, we use a measurement metric called AUC, or area under the curve. Again, you can look up the precise definition of this, but think of it as a higher area under the curve means that you're in a better position to identify the target condition that you're looking for. When we generate predictions with numerical variables, the actual numerical prediction is the output. With a categorical variable, we have two outputs. One is the categorical prediction of what the dependent variable is, and second is the probability that it's in the target class. We'll see an example of this later. Finally, when you evaluate the predictions for accuracy, for numeric variables, what you're trying to determine is what was the distribution of prediction errors. With categorical variables, there are 2 things you're looking for. One is how accurate were the predictions. So if you said the answer was true, what's the likelihood that it was true? The second is, did your model find most of the targets? So how was the number of your true answers compared to the total number of actual true answers? And we'll see examples of this as we go into the actual case studies. Today we're going to be looking at 2 case studies. We've chosen publicly available public domain data for the examples. The numeric data is one where we estimate the number of miles per gallon that an automobile will achieve. The categorical example is a wine example. We look at different kinds of wine and determine whether it's a high quality wine or not based on various chemical attributes of the wine. So now let's get into the cases. Let's begin with the miles per gallon example. In this data set, we predict the miles per gallon of a particular vehicle based on various attributes and characteristics of the vehicle. We've already loaded this in, and we can see that the predictive score of 0.73 or 73% indicates a pretty good likelihood that this model has predictive accuracy. So let's look at the models that Prophecy has tried. If you look at the page here, you can see that there are 3 different models that have been checked by Prophecy: extra tree regression, decision tree regression, and gradient boosted regressor. The mean squared error, which is the metric which it's using to evaluate these different models, in the case of extra tree regression, is 16.9. In the case of decision tree regression, it's 23.8. And in the gradient boosted regressor, it's 25.9. At 16.9, extra tree regression is clearly better than the other 2. What does that mean? That means that the distance between its predictions and the actual values is smaller than with the other 2 methods. Let's take a look in a little more detail. I click here on the performance analysis button, and it takes me to this screen where it analyzes that particular method. The graph here shows the MSE for different crossfolds, and I'll explain what crossfolds mean in a second. The line across 16.9 is the MSE for the entire database. Now, in crossfolds, what Prophecy does is it takes a percentage of the sample. In this case, it takes roughly 20%, or 80 out of 397, develops the model using the remaining 317, and then looks at how well it did in predicting the 80 that were held out, as the term goes. And it does these with 5 different holdouts. So 5 different times it takes 80 different records at random, uses the other 317 to predict. And the results can be seen in this graph up here. So you can see that a couple of the crossfolds did much worse than the average of 16.9, but 3 of them actually did better. One of the reasons this varies so much is because this is a relatively small data set with only 400 data items. With a large number of data items in the thousands or tens of thousands or perhaps much more, we would expect to see much less variance than this. So let's go back to our original screen. Extra tree regression performed much better than decision tree regression or the gradient boosted regressor. So to us, it appears like the best method, and it's the best method according to Prophecy as well. Let's now move to the actual prediction screen. We click on the Activate tab, and what we see here is the current feed that we're using. It allows us to select the model, so we could use any of the 3 that we looked at or allow Prophecy to select. And we find a training model. In this case, I select this file, mpg_data_train, which is a new data set, and the model that we used will predict, based on the new data set, what the value should be. Open. And when we press test, it generates a new file. Let's go and take a look at the new file. Here's the prediction file that Prophecy generated. Column M is the actual prediction, and the columns to the left are the original data repeated here verbatim. You can do some additional analysis on this, so let me show you what that might look like. Here we've added 2 columns. Column O is the difference between the actual miles per gallon, which is column C, and column M, the predicted miles per gallon. In column P, we've converted that to a percentage and taken the absolute value. So in the first example, we have a predicted value of 19 miles per gallon versus an actual of 17.6. So the difference of 1.4 results in 8.13% difference. If we go further down, we can see a range of differences, 8%, 13%, and so on. We have one very large difference in row 13 of 50.51%, but we also have some very small differences, 3%, 3.22%, and so on. We compile these into a histogram to show what the distribution of the errors were in terms of frequency, and we put them in different bins, from 0 to 5% error, 5 to 10%, 10 to 25, 25 to 50, and greater than 50. And you can see that the great majority of these were in the range of much lower than 25% or lower. 42 of the 48 items that we had in the test database were 25% less in error. And a small number, 6 out of the 42, were greater than 25%. Now, whether that's a good predictive accuracy or not depends to some extent on the problem that you're trying to solve. But in this case, we felt that was quite a good predictive accuracy. Now, let's look at our wine quality analysis. We've already loaded the data set, and you can see that with a score of 0.853, there's a high level of predictability in this data. Let's look at the models that Prophecy has generated. In this case, it's looked at 5 different models. The AUC, or area under the curve, is the performance measure that it uses to rank the models. The top model in this case is the gradient boosted classifier, followed by the other 4. Gradient boosted has a performance metric of 0.856, and the others have progressively lower than that. Let's take a look at the scores that it's laid out at the analysis. This is telling us that the AUC for the entire population is 0.856, but the crossfolds have different AUCs ranging from 0.787 to 0.91. You can see that the variation is fairly close. We don't have a lot of variation within the folds. And again, the crossfolds were done in the same way as we showed in the continuous example. There was a holdout of 280 observations for testing. The total number of observations for training was 1,118, and it did 5 crossfolds. Let's look at another measure of the accuracy of this modeling. So in this case, we're particularly interested in something called the confusion matrix. The confusion matrix essentially shows us of the predictions for positive, which ones were actually positive, and of the predictions for negative, which ones were actually negative, and which ones were wrong in both cases. Of the 5 folds, the best prediction that we came up with we predicted 215 were of high quality, and they actually were. We predicted that 40 were not of high quality, and those actually were. And there were 13 and 12 respectively where we made a prediction and turned out to be wrong. And you can look at the worst accuracy. In this case, we had 51 total that were wrong and 229 that were correct. So a fairly good level of prediction, which is why we saw such a high score at the beginning. Let's go back and generate the predictions for this data set. I'll pick the wine high quality train, open the file, and once again, generate the predictions. Let's now take a look at the predictions that the system has generated. We are looking at the prediction file for the wine example. Once again, it has replicated all the input columns from the test data. It has also added 3 new prediction columns. Let's go through those prediction columns so we can discuss what they mean. Column N is the original wine quality indicator from the test data. It's called is good quality. Column O is Prophecy's prediction based on the test data. Column P is called is good quality predicted labels, and if we had set it up to put out readable labels such as yes or no or true false, they would show up in this column. Since we didn't make that selection, it just repeats what's in column O. Column Q is called is good quality relative probability. This number is used to make the prediction in column O. So if we look at the first row here, 0.483, since it's less than 0.5, our prediction is 0 or negative. If we look at the second row, it's 0.774, which is greater than 0.5, and so it makes a prediction of 1. So we use this threshold of 0.5 to make these predictions in this database. Now, let's talk about how you can interpret these predictions. Using Prophecy's predictions and a 50% threshold, we prepared this confusion matrix. Since this was a test data set, we had the actual results to compare it against, and it's very useful during the testing process. If you're using it in ongoing production, you probably won't have predictions to compare it against at the time. You may have to go back after the results were tested and real results came in to prepare this confusion matrix. The test data set had roughly 1,400 observations. And of these, in actuality, 275 were high quality wines. If we look at the predictions that resulted at the 50% threshold, we predicted that 383 of these observations were high quality wines. 153 were accurate. So in other words, roughly 40% of our predictions were accurate. 153 out of 383. This is double the base rate of 20%. Roughly 20% of the wines observed were high quality. The second metric that's of interest is the completeness. Completeness indicates how many of the high quality wines did we identify. In this case, it was 153 out of 275, or 56%. We ran this again using an 85% threshold. 85% threshold meaning if the probability was greater than or equal to 85%, only then would we make a prediction that the wine was high quality. So in this case, we predicted 222 wines were of high quality. Our accuracy was higher. 106 of those 222 2 were actually high quality. Our completeness, however, was lower. Only 39%, or 106 out of the 275, were high quality. So you can see in this simple example that there's a trade-off between being accurate and being complete. Now, which side of the trade-off you want to be on depends on the data set and depends on how important it is to identify positive attributes or negative attributes. It depends on the economics of the case and the specific data set.